Let me just introduce then today's session. So thanks all of you for your patience. Most of you, I think, have probably found this. The chat feature, by the way, is the feature that enables us to, or rather you to contact panelists and all attendees. So make comments, but if you'd like to address specific questions, please use the Q&A feature, okay? And the presentation will divide into 3 sections, approximately 30 minutes each. And after each section, we'll pause for Q&A. And I will select some of the questions from the Q&A feature to address to Sri. So it's my pleasure to introduce Sri Krishnamurthy, CFA, the founder of Quant University, a data and quantitative analysis company, and the creator of the Analytics Certificate Program and the FinTech Certificate Program. Sri has more than 15 years of experience in analytics, quant analysis, stats modeling, and designing large-scale applications. He earned a Master's in Computer Systems Engineering and a Master's in Computer Science from Northeastern University, and an MBA with a focus on investments from Babson. So in his presentation, Sri will build on the session that we ran last week. If you haven't had a chance to see it, you can either search for it, just Google CFA Machine Learning Introduction Krishnamurthy, and it will come straight up, but also post a link within the chat function for you to use. If you haven't had a chance to see it, you'll still find there's value in today's presentation for you, because I know that Sri will be doing a little bit of recap of the session last week. So thanks for that, and over to you, Sri.
Thank you so much, and thanks again for the patience. I'm so sorry about the internet issues. You know, there are only certain things in life we can control, as we can all imagine in the day of COVID-19, I guess. Can I share my screen?
Okay. Please do.
Okay, so in the interest of making sure that the network bandwidth is saved, I'm just going to go with the presentation and the demos, and during the Q&A, I will bring back the video. So thank you again for attending today's session. As Richard mentioned, my name is Sri Krishnamurthy, and I'm going to be the facilitator for today's session. So as Richard mentioned, I've been working in the intersection of quantitative finance, machine learning, and data science for many, many years now. And the 2 sessions we have planned for the CFA Institute is primarily to give you an orientation on what AI and machine learning is all about and its applications in finance. I am also a professor at Northeastern University, an adjunct professor at Northeastern University, wherein I teach data science and machine learning, and I've been teaching it since 2013. And I've seen the whole field evolve significantly over the last 6 to 7 years. And many of the lessons I've learned primarily from my students, because they have been doing amazing projects and they've been telling me like all the fun things which are happening in the world. And then when we go and look at all these technologies, it's a lot of details to be kind of looked at, because you have a lot of packages, you have a lot of applications and case studies, and you have to really practice to get a good feel for what these applications bring to the table. And that was the whole reason why we created Quant University, to primarily help bring in the discipline of rigorous research and figuring out what actually makes sense from an application perspective. So I'm not going to be using a lot of vendor products or packaged solutions out of the box today. So I'm going to go under the hood and tell you a little bit about the various technologies and the various methodologies which are typically used. So in today's session, I'm going to quickly do a recap of what we did last week, primarily giving you a 60,000-foot view of what we covered in 2 hours and maybe 2 to 3 minutes. And then we will dive into today's session. So for people who missed the first session, so we primarily talked about the key trends in artificial intelligence, machine learning, and finance. And then we looked at some of the key technologies involved, and also looked at the methodologies which are primarily used when we talk about machine learning and AI. And we did a couple of case studies to reinforce those concepts we had learned in the class. And we did 2 primary case studies. The first one was predominantly in the realm of credit risk, and we talked about how you can use readily available public data to build out machine learning applications. And we used a credit risk modeler to figure out how you could use different machine learning methodologies to build an interest rate predictor. Then we kind of looked at the whole area of synthetic data and how people are using synthetic data for various applications. And we looked at a couple of applications. One was to generate data for augmentation and also for anonymization. And then we looked at another example on generating what-if scenarios using the sales generator demo. And then we looked at another case study wherein we could generate synthetic VIX data using some neural networks. Primarily, we were building upon this whole notion of how do we build out a machine learning workflow? And what does it mean to look at the whole pipeline, if you will, in the context of bringing in data from either publicly available data sources or through databases and taking them through the process of building out applications. So we will continue working with this framework today, but we will do a little bit of a deep dive in some of the methodologies which hasn't been covered, which we weren't able to cover in the prior session. So what are we going to be doing today? Well, before I get there, just to kind of talk about the slides and the video and the demos which you just looked at, we have a site called academy.qsandbox.com. You can use the code CFA Masterclass, and everything is in one place, so you can access the demos I showed last class for you to test it out yourselves to get a better feel for these applications. We just saw that there were people from 24 countries who have logged into the system and they have looked at it, so you're welcome to kind of take a look at the prior session. And today's demos and today's slides will also be posted on the same site. Okay, so let's do a deep dive into today's session. As Richard mentioned, we're going to be doing it in 3 parts. And the first part is going to be a deep dive into some of the machine learning methodologies and core applications. First of all, we looked at some of the supervised learning methods in the last class. And today we're going to focus on unsupervised learning. And we talk about some of the methodologies used in the unsupervised learning realm. And then the second thing we're going to do is look at supervised machine learning, and we'll use classification as an example. What we're trying to build today is a baseline and a foundation for some of the case studies which we're going to discuss. And the first case study will take publicly available Dow Jones data sets, and we'll look at different clustering methodologies, and I'll tell you the various levers you'll have to deal with when you're working with clustering. Clustering is not always k-means. People confuse clustering to be a simple k-means algorithm wherein you just give it k and give it the data, and it's going to give you these beautiful clusters out there, and we just need to make a choice of which clusters to use. It's not as simple as that. Unsupervised learning is a very hard problem. In fact, it's harder than a supervised learning problem because you have no labels to work with. So then we will talk about natural language processing. A lot of interest, a lot of evolution has happened in the context of processing language, and the whole notion of working with unstructured data is becoming extremely popular in the financial industry. And we'll talk about a simple application in the context of sentiment analysis. And I'll tell you of some of the tooling which is readily available out there. And without you having to delve through the linguistics textbooks, without you having to understand the grammar of a language, without you having to understand all the neural networks and BERT and all the complex models people are talking about, how can you start building simple applications with machine learning services as an API is something we're going to look at. Then we'll talk a little bit about some of the frontier topics after the second break and how machine learning is kind of evolving over time. And that's going to be the plan for today. So I hope you enjoyed today's session. So let's get going. Let's start with a quick refresher on the framework. The framework we talked about involved 2 parts. One is processing data and then thinking about the modeling piece. The top 4 boxes focus on processing the data pieces, and the bottom 4 boxes talk about how do you actually model your application. The same framework works for both supervised and unsupervised learning problems, because when you start working with the problem definition, you have to think about which models do I use and how do I bring in the data, and then you're going to choose and you think about the right methodology in order to work with based on the problem you have at hand. So let's kind of delve into some of the core methods. As we mentioned last time, there are these category of algorithms: unsupervised, supervised, reinforcement learning, and supervised. Since this is an introductory session, we're going to primarily focus on unsupervised and supervised learning problems. And last time we talked about the various things you could potentially do. So today we're going to focus on the bottom right corner of this whole flowchart, if you will, and start talking about some of the prediction you could potentially do in the context of classification. Okay, so as we mentioned, supervised learning problems typically have data sets which are labeled, and typically the variables which we are going to be using to build the model will be marked as x1, x2, x3s, and the label will be marked as y. And if y is a number, we call it a prediction problem, and if y is a class, it's a classification problem. So the problem we're going to do in the context of the case study later is, given a particular review or given a paragraph of text, how do I determine whether the author's or the speaker's sentiment was good or bad? So good or bad are two different classes. So how can you go about building out a model in order to do that is the problem we're going to try and address. So in the context of algorithms, there are multiple algorithms out there. And as I mentioned, we're not going to go into the mathematical details about the model, but you may have heard about some of these models when you got exposed to machine learning in the last class or through other channels. So the primary parametric models which people talk about are things like logistic regressions and neural networks, which basically means that when you train your model, you're going to get a bunch of coefficients. And using those coefficients, you're going to be doing what's called as inference, which is trying to figure out, given a new set of data, how can I build a classifier which is going to tell me what the labels are going to be, right? Now, there are other kinds of algorithms which are non-parametric too, things like KNN and decision trees. And here, the notion is, instead of me trying to build out a bunch of parameters, how about I build out the algorithm in such a way that either there are some decision rules or some ways in which I can split the data, and that's going to evolve into my classifier, which will help me make a decision based on the inputs. How can you define the various classes? So I'll give you a little more details on these algorithms, but the big picture view is, in the supervised learning algorithm classes, you have either a parametric model or a non-parametric model. Now, on the other hand, when you talk about unsupervised learning models, you don't have labels, unfortunately, and that's a hard problem, because if you do not have any labels, you don't know whether the model you're going to be building is going to be usable or not, because there are very few ways in which you can figure out whether the model actually works or not. But that doesn't mean that you are stuck with not doing anything. There are various things you could potentially do with unlabeled data sets. And one of the classic methodologies people talk about is what is called as clustering, which is to build a model, taking the various observations, and then segmenting out your data into multiple classes or segments. And there are various ways in which you could potentially do that. But typically when people talk about unsupervised learning algorithms, clustering is one of the core methodologies which are being used. So what do you, last time when we talked about supervised learning algorithms, I gave you some details about how could you potentially use regression and other methodologies. So how does an unsupervised learning algorithm work in the first place? So I'm not going to give you a lot of math in here, but I just want to give you this intuition on typically what actually happens when clustering is done. So when people talk about clustering, we need to talk about distances. And what that means is, I'm trying to figure out if there are two observations which are similar to each other. So in the context of financial services, are two stocks similar to each other? Or two bonds similar to each other? Are two sectors similar to each other? Are two countries similar to each other? So those are the questions we need to start asking. How do you define similarity between two classes in the first place? And clustering is a technique wherein you could basically take data and the various variables or the features associated with the data, and then think about bucketing them into similar buckets, right? So for example, this algorithm called k-means comes up with this proposition that you tell me how many buckets or clusters you want, and I'm going to use a distance metric which you will give me, and then think about ways in which I could figure out the similarity between these objects and then classify them into simple buckets. So the analogy I give is, if you have balls of different colors and you have different baskets, you look at the color and you put it in one basket, and you take, look at the ball again, and then you put it in another basket. So you're using color as means of figuring out whether the red and the orange and the pink balls all need to be in one basket, and the greens and the blues and the purples need to be in another basket. Similarly, we are going to be using various numbers and categories to figure out similarities between these objects and then build out our clusters. Now, what does it mean by figuring out similarities? So there are a lot of ways in which you can define similarities, and one of the methodologies is to just compute the distance, the Euclidean distance between 2 points. So it's like taking a measuring tape and then taking 2 points and then figuring out what the distance is. And that becomes pretty simple if I have just numbers. But what in case you have things like time series, which are typically what you're going to be dealing with in the context of financial data, right? So stock has certain price, vector of prices you have captured over time, a vector of returns maybe, a vector of closing prices maybe, VIX returns over time, et cetera, et cetera. So how do you define similarity is the question we're going to try and answer in the case study we're going to discuss. And one of the ways to look at it is thinking about correlation. So you figure out if two series of data sets are similar to each other, if they are highly correlated with each other, is one of the ways in which you can think about distances. Now, I'm going to start giving you a couple more methodologies in the context of unsupervised learning, because this is a core methods class, and I just wanted you to be exposed to some of the terminologies you will hear before we actually dive into some of the applications. Another clustering methodology is what's called as hierarchical clustering. And that's where you're going to try and figure out, well, can I build out a tree of various, if I start looking at these objects, instead of just putting them into discrete buckets, can I build out a tree in such a way that the leaves and the node at which they kind of, converge, so they are all part of one cluster. And then this notion of bottoms up clustering figures out, like, if I can figure out these small buckets which are similar to each other, and then start building the linkages, so that I can build out a complete tree, so that I start from the bottom and start from the leaves and build out the whole tree, inverted tree as you kind of build it up. So that's the algorithm which is typically used for hierarchical clustering. It's a very popular method when you talk about clustering. One is k-means, and another one is what's called as hierarchical clustering. And we'll talk about how this can be implemented as part of case study in a little bit when we work on the case study. Another method which people have been looking at is what's called as affinity propagation. And it comes with an interesting paradigm on figuring out how you can pass messages between various data points. And the goal is to find exemplars or members which represent these clusters, and then start building out these clusters based on this algorithm. And this is a little more complicated algorithm than the typical k-means and hierarchical clustering algorithm you would typically be exposed to in a basic textbook. But I just wanted to put in there for you to let you know that there are various algorithms or methodologies which are used in the context of clustering, and not just the simplistic k-means and hierarchical clustering which you'll typically be exposed to. And when we do with the case study, we will delve into some of the details as we go through the case study. Okay. People always talk about clustering as the unsupervised learning methodology, but you may have come across other unsupervised methodologies when you kind of work with financial data or other quantitative data sets. And I'll briefly expose you to a couple of these methodologies. We'll not delve into the details, unfortunately, in this session. The one is the classic principal component analysis, or the PCA. It's a dimension reduction technique. Typically, if you have a lot of features and you want to reduce the number of features, what you do is you basically reduce the number of components. That way you can work with fewer derived components rather than working with all the original components in the first place. So that's basically what's called as principal component analysis. There are other complex methodologies. One is what's called as manifold learning. And here we do dimension reduction, but in a non-linear way. And that's another example I'm going to illustrate as a part of the case study. And another classic one is what's called as market basket analysis or association rule mining, which you probably have used when you have bought books on Amazon. People who bought this book also bought these other books. So this is where, by looking at the data, you will be able to factor in data from one element and say people who bought something also bought this other basket. So you start building these rules and start putting together these rules and then start enforcing these rules as part of your unsupervised learning algorithm. So as you can see, the whole area of unsupervised learning is a very rich field, and there are multiple methodologies involved. And people typically start looking at supervised learning problems as the place to go to start out with machine learning. But when you start expanding your purview of what all can potentially be done, there's a whole rich field of opportunities to use various methodologies and techniques to enrich your analysis. And we'll look at a couple of examples later in the session. Okay, so when we talk about how do we implement all these things, people start wondering, well, am I stuck with the traditional logistic regression algorithms, or do I have other options? And in today's day and age, neural networks is becoming extremely popular. And people have been using this notion of deep learning, and deep learning is becoming extremely popular in finance too. And the notion here is, rather than just thinking from a modeling perspective and making all the assumptions with respect to the data and thinking about linearity and thinking about the constraining the problem with the way in which we can think about, we let the algorithm binge on data. So we give it a lot of data, we give it a lot of compute power, we give it the flexibility to figure out maybe millions and millions of parameters for a particular model instead of just a few regression parameters, and build this really deep and dense networks, which will help us uncover the relationships in the data. And the reason why I'm mentioning this to you is, if you have been exposed to some of the latest modeling practices in the world today, many of the traditional methodologies like regression and decision trees have been around for a while. But in the last 5 to 7 years or so, neural networks has made a significant impact in the way we do modeling. And you're going to see a lot of neural networks being used, and either as a machine learning as a service or through packages like TensorFlow and PyTorch and things like that. So here, you are going to see a lot of unsupervised and supervised learning algorithms. And when we talk about autoencoders, it is basically an unsupervised learning methodology to do dimension reduction and then kind of build out ways in which you could represent the data. But then you could also think about using a CNN or a convolutional neural network to build out either a classifier or a predictor. You could think about using an LSTM or a long short-term memory network to work with time series related data sets, so that you're not only looking at cross-sectional data, but also factoring in the temporal nature of the data. So there's a whole suite of modeling opportunities out there, leveraging model-free methodologies by which you could just basically use levers to control the number of layers and control the number of nodes and build out algorithms which you never thought would be possible with the compute infrastructure and the algorithmic infrastructure you had just a few years ago. So it's something which is going to revolutionize machine learning in the next few years, and it has already revolutionized significantly our lives. Think about our Alexas of the world, the Siri of the world. They're all predominantly using machine learning methodologies built on neural networks. Think about auto-completion when you write your Gmail, or when you think about replying back on LinkedIn, it gives you suggestions based on what you have just input. All those text-based applications are heavily using neural networks to determine the response or to generate text as we speak. Think about translation engines when you think about traveling in a foreign country and you use your mobile device to make a statement or put out a statement in English and want it to be translated to Spanish. So their translation is happening using neural networks and various other methodologies. All the driverless innovations which are happening in the context of autonomous driving, detection of various objects, your Nest and your Google now, all these things which are kind of permeating our lifestyles are heavily reliant on neural networks. And guess what? Finance is also going to be revolutionizing itself with applications of neural networks in the near future. So it's something to keep your mind open with some of the methodologies out there. And there are pros and cons of using neural networks. And when I talk about risk in the context of machine learning at the end, most of the work we have been doing as an entity in the last few years has been helping people decipher the complexities of neural networks and what neural networks actually mean, because it's in some ways a black box and you don't really can get under the hood to understand what's actually influencing the outputs. And you had to think about interpretability, you had to think about governance, you had to think about risk, and all these key aspects when you're building neural networks. So there's a lot of innovation happening, but there's also opportunity to further innovate because neural networks has a lot of power, but we still haven't really understood all the key aspects of what it can potentially do. And AI, when people talk about AI, heavily, a lot of neural networks is being rebranded in the context of AI because when people talk about intelligence, all these methodologies would come in together when we think about building out systems which can leverage neural networks and rule-based engine and various other methodologies. Okay, so I just wanted to give you a big picture orientation on some of the key methodologies which are out there, especially in the context of machine learning when you're kind of working with various kinds of algorithms. And as I mentioned before, the framework we have, we are kind of looking at top down. If we are looking at a machine learning problem, how can we segment out the world? And in last week's session, we primarily focused on this side of the puzzle, which was supervised learning and doing prediction, credit risk, and maybe even doing mixed generation. Primarily, it was focused on this side of the puzzle. And in today's session, I talked a little bit about classification and unsupervised learning algorithms, which was on this side of the puzzle. So you now have a good understanding of what the supervised kind of algorithms are for prediction and unsupervised learning algorithms are for different kinds of applications. And when I do the case studies, you'll get a better idea of how this would come into play. Now that we have the algorithm choices, by the way, there are a lot of different ways in which you could structure the problem too. And when we do the frontier topics, we'll revisit this area about some of the methodologies out there. So I'll skip the slide for a minute in here, but we'll revisit as we go through the session. So now that we have an algorithmic choice, what do we typically do when we build out our pipeline? And I'm giving you the recipe. Think of this as like the default cake recipe, if you will, right? So you don't have the flavors yet, but you need to understand the process of how are you going to be baking the cake? What are the ingredients, the core ingredients you need? What are the utensils? What is the temperature? You're kind of getting an orientation of all these things. And when we start baking the real cake, all this will come into play. But bear with me when I'm kind of giving you these concepts because you will need them when you put together your entire pipeline. So the process which we're going to go through, as I mentioned, will curtail it a little bit in terms of scoping. Most of this is data handling. And here is where we are building out a model and selecting out the model. So now that we have a model we have chosen, either in the context of classification or in the context of unsupervised learning, how do you evaluate whether a model is good or not? So last time we talked about mean absolute error, mean absolute percentage error, et cetera, as ways in which you could evaluate a prediction algorithm. I want to introduce you to a couple of new concepts today. In the context of classification, there is this notion of confusion matrices, which are typically used for figuring out whether a model is good or not. And then you also have ROC curves. Now, believe me, when I teach my class to my students, either at Northeastern University or in a professional setting, usually my students are very excited till maybe the last slide, because they all want to build the models and then move on to the next big thing. No one wants to figure out whether the model is working well. Can I fine tune my model? Is my model performing really well? And all that good stuff. Because in life, we always want to go for the exciting things, right? So we want to look at the best algorithm. We want to look at newer flavors of the algorithm. But we don't feel like tweaking and tuning these algorithms. But guess what? In the real world, in order to generate value from what you've been doing, it's not about the diversity and the variety of algorithms which really matters. It's about the robust processes you're going to set up so that you have really good control about how you're building out your process and how you're evaluating how good you are. Especially in times of crisis like what's happening now, when you have significant volatility in the markets, and if you have a lot of machine learning algorithms which have been built with data which has never seen real volatility in the past, you're going to be dealing with a model which is stale. And if you are not evaluating your model and figuring out if your models are fresh enough, you're going to be making decisions as though you had only information of yesterday. So it's very important for you to really understand these performance metrics as you kind of go building out your machine learning algorithms. And I'll give you a couple of measures out there, but there are a lot more measures which I would like you to really focus on as you build out your machine learning process. So a couple of things to note, when you think about, let's say, building a classifier, we are going to look at this notion of classification metrics, which basically talks about, well, these are the actual observations of things I've seen in the past. And if I use the model using my X values, what are the predictions you're going to do? And then I'm going to look at what was recorded in the past and what my model predicts, and then compare and contrast whether my model is doing a good job or not. It all depends on the use case, because in certain cases, you want to figure out whether I'm getting the yeses and my model saying yeses very close. That way I can make sure that my model is a good yes predictor. In certain cases, I want to predict a no. And depending on the use case, I have to choose the right metrics to fine tune my model. And there are also a lot of different ratios like F1 scores and things like that you'll have to think about depending on the use case you have at hand. And it's a very rich field. And in fact, the confusion matrix Wikipedia entry is one of the most beautifully written ones because it details a lot of different varieties of ratios you can compute and the metrics you can compute in the context of classification metrics. So here are a couple of samples. So if I wanted to figure out the overall error rate, I'm going to look at adding up all the numbers in the 4 boxes as the denominator, and then looking at only the accurate ones in the top or the numerator. And overall, I'm going to figure out how accurate was I in terms of prediction based on all the observations I have. And that's going to give me the overall accuracy metric, which is also going to be 1 minus the error rate I'm currently observing as a part of my modeling exercise. So this is a very simplistic measure, but accuracy may not be the measure, especially if you're working with algorithms which are doing things like anomaly detection or fraud detection. Because at that point, the minority class is the most important one and not just the overall big picture measures. There's also this notion of an ROC curve, which people talk about. And there, you're going to be plotting your X and Y axis. Your Y axis is what's called as true positive rate or sensitivity. And on your X axis, you're going to have 1 minus specificity, which is basically specificity is the true negative rate. And my goal is to build out an algorithm which is going to hug somewhere very close to the y-axis and becomes flat on the top. So the area under the curve, the higher the area under the curve, the better my algorithm is. So people use these kinds of graphs to evaluate whether the algorithm is good or not. And a random choice would be somewhere along the diagonal. Because if your model says that my prediction is very close to the diagonal, you may as well live with a random predictor rather than using your algorithm in the first place. So there are a lot of interesting metrics you could potentially look at. I'm not going to go into a lot of details as a part of this session, but I just want to emphasize that do not stop at just looking at the models. You have to look at the performance measures and what does this actually mean. And the reason I'm telling you this passionately is because I've seen a lot of novice and novel users of machine learning go into package systems, which are typically point and click. And they just pass in the data, choose an algorithm, generate the outputs, and move on to the next thing. They don't spend enough time really understanding the metrics, either in the context of training accuracy versus testing accuracy, whether you're overfitting or how do you address bias in various places. So there are a lot of different things you could potentially do to fine-tune an algorithm. And you need to be really aware about what it actually means to understand the process and make decisions based on it, rather than just being a user of prepackaged solution. So please be very careful when you're choosing results, because that's where you're making the biggest decision, which is figuring out how you're going to be trusting your model as you go into production. Okay, so now that we have the various key pieces, we have looked at the data, we have looked at the goals, we have looked at various machine learning algorithms, we have understood the process, and we have evaluated the algorithm. I think we are ready to build out some of our examples, which is where we're going to start kind of operationalizing this methodology, which we kind of did last week and this week, and talk about how you can apply them into specific practices. So Richard, I'm going to take a break in here. I know we have covered a lot of material in a very short period of time. I'll take a break in here and answer any specific questions your audience may have.
Okay, perfect, Sri, thank you. So yeah, quite a few questions have come in. And by the way, we won't be able to get to all of your questions today, but we will try to get to at least the bulk of them post the session. But there's a theme here around explainability.
Sure.
When you're using, say, a neural network. And there's a few different points made. I mean, what if I'm dealing with a client and let's say there's a recommendation that this is a good stock based on my neural network? How do I explain this to the clients? Right. Is there a model or methodology for explaining how neural networks come to their answer?
Right. So it's an active field of research, explainability in the context of neural networks, and unfortunately, it's not a solved problem yet. There is, every time you go to a conference, you always see different methodologies on how these various layers are inferring different parts of the world. In fact, there are some nice papers in the context of computer vision, and which say something like, and I think this is a popular paper called "What Do Neural Networks See?" And that kind of talks about how individual layers are inferring various pieces of the puzzle as it's building out its classification. Explainability and interpretability of models is becoming a very hot topic, especially because in the context of model governance in financial services. So you have different layers of explainability. Am I explaining it to the model governance people because we are trying to factor in all the risks which are potentially lingering in our models, which we don't really understand, which are black boxes in the first place, right? But as a fiduciary, I need to be also taking care of my clients' interests, which is the predominant thing I have to do. And I have to explain to my clients what are the methodologies I'm using to make these decisions. And it's not only about marketing, saying that, hey, I'm using these cool neural networks and AI-based methodologies. It's also convincing your clients and convincing yourselves in the first place that you really understand and you're doing a good job in terms of taking care of your client's interests. So that's where explainability there comes in the context of, do we really feel comfortable that we have the required in-house expertise to trust these models? How much backtesting have we done? How much do we understand the scope of these stress tests or the what-if analysis we have potentially done? How, if we take this model and apply it into stressful situations in the past or synthetic situations in the past, how will our model perform? So all these are, things you may have to potentially ask. In certain ways, there's also the flip side of the coin, like, do we need to understand everything in order to start using it? And the analogy there is, well, can we explain all our decisions as humans, right? So humans are very complicated creatures, right? So we are making decisions on a daily basis based on our assumptions of the world, based on the way we kind of infer things. And similarly, models could potentially be trained on data sets which the model thinks that's the world, and if the data is not rich and diverse enough, it'll have a perspective of the world which based on the data it has seen. So all those need to be thought about. But there are some really nice publications, and if the person who asked the question sends me an email at info@qsandbox.com, I'll be happy to share some more resources.
Excellent. Another theme around questions actually is just how you make choices around the models or techniques to use, which you've been trying to talk through. So I'm going to put you on the spot a little bit here, and maybe you can decline to answer this one. But question is, what model or technique would you utilize to help understand the spread of the current pandemic?
Yeah, so there's obviously a lot of questions, and the data itself is not fully available out there to model these things. But I think Marcos Di Prado and Alex Lipton wrote a recent paper, and that has, they've done some presentations in the recent past too. On SSRM, there is a paper where they try to model the pandemic. So you could potentially look at different methodologies in which you could do it. And I think Marcus is now advocating this whole notion of now casting, instead of just doing back testing. So that's another methodology you could potentially use too. But again, it's a novel field. People are, in fact, you go into any research SSRN publication, everybody's tagging in COVID-19. You have to do the sifting, whether it's just using it as a branding or really doing something in the context of modeling these pandemics. But there is a lot of network science involved in here too, not just traditional forecasting, leveraging historical data and building it out. So you have to look at a lot of network science related aspects in the context of complexity theories and modeling things happening in one part of the spectrum affecting other parts. I think Professor Barabazi at Northeastern University has written some really cool books on network science. So that's another area you may also want to think about when you're trying to model pandemics.
So Marcus C. Prado has got some good work on this, yeah?
Absolutely, yeah.
Okay, excellent. That's very helpful. That's good to know. And one last question. Do you see neural network outputs being used as inputs for other neural networks?
Absolutely. In fact, that was this was a few years ago when the whole CNN was being discussed, the convolutional neural network. So people had thought about using one neural network to do basically what's called as feature extraction. So instead of you trying to build out all the features yourselves, let a modeler or let a neural network like autoencoder, kind of figure out the reduced dimension space of your features, and then use the reduced dimension space of your features as an input to a CNN or a new neural network. So that was kind of the methodology people were originally thinking about. But later, people said, well, we could actually integrate both of them into a neural network and kind of build out the neural, because the neural network itself, it doesn't come with definitions, right? So you can actually daisy chain multiple components. So many a times what happens is the feature extraction is the major component in figuring out like the relationships between various variables, and then figuring out what am I going to be doing with these features. Either it's a classification or regression kind of a problem. So that's where you kind of decide what should I do with all these reduced features. So you could use outputs of neural networks into other neural networks. However, you have to use it with a bit of caution. I was actually having a debate with someone on LinkedIn recently, and that was where, if you use a neural network, a synthetic data generator using GANs or generative adversarial networks for generating synthetic data, and now you are actually working with artificial data and using that as an input to another neural network. Well, there are pros and cons. If you're augmenting a piece of the data set which was not observed in the past, and you're basically modeling it, figuring out pandemics or stressful situations, and then augmenting it with prior observed classes so that your neural network is aware of the new world wherein these extreme situations, even though they were not observed, were possibilities, then it's an appropriate use case. But if you're just kind of taking in a model and generating outputs and then putting it to the next model without really understanding the big picture, garbage in, garbage out. So you're taking garbage coming from one processor, putting it into another one. So you can't expect really good things at the other end.
Okay, perfect. Thank you. Right, back to you.
Okay, perfect. So let's kind of, I'm going to share my screen again. Let's get back to the second part of the presentation. And here I'm going to do a couple of demos and give you a little bit of a perspective of, how can you actually use all these techniques which I've mentioned. So I'm going to give you a little bit of motivation in the context of clustering of stocks. And my goal is to not give you, a formula or a recipe saying that take this and this is what's going to work. Because I want you to be able to appreciate the richness of the ecosystem which is out there. And we have just chosen the sample problem to get you a feel for the possibilities, but you have to do the due diligence because I don't know your data, and just taking this methodology and applying it to your data is probably not going to work. So we're going to take a very simplistic use case of using Dow Jones data sets so that everybody has access to the data, everybody can reproduce this experiment, but you have to contextualize it and use it in your application. The motivation for this particular case study, and we'll kind of do it in 4 steps. We'll introduce the case study, we'll do some data exploration, and we will build out the model, and then we'll deploy it, and we'll illustrate how it's potentially done. And the motivation of this is, well, as you know, the world has so many potential assets you can invest in. And if you are working with mature markets, you have a very rich, categorization of various sectors, classes, countries. You have the various boxes which you can put these stocks in. And then as a portfolio manager, as an investment analyst, you can figure out how you can potentially choose assets from different buckets and work with it. However, at times, all assets don't behave to the bucket in which it was originally assigned. Certain times, growth stocks can act like value stocks can act like growth stocks. If you're working with emerging markets or frontier markets data, you don't even have a rich classification of data sets. So you'll be wondering, well, how do I even figure out these data sets? And if I'm working with a really large universe, are there methodologies rather than me individually looking at time series and getting an understanding, but not really understanding a deeper picture of how are these associated with each other? Clustering and machine learning could be a very good decision support tool, which will help you with your analysis or your investment process. So that's kind of the motivation of why this kind of came into play. So we want to be able to answer questions are, which stocks are like each other? What's the similarity? And I'm going to tie this notion to this notion of distance we talked about earlier about clustering, wherein there were various kinds of distance metrics. And we want to try and understand if 2 stocks are meant to be similar, what are we looking at, right? And then I mentioned this a little bit ago. So, how are growth stocks behaving like growth stocks, or are they behaving like value stocks? And then, if there is a time series of returns or prices, can I just use that information to figure out if stocks are close to each other? Should I look at other metrics on base in which you can look at time series if they're close to each other? So these are the kinds of questions you may want to start asking if you're planning to use clustering for your investment analysis. Okay, so to set up the problem, I'm going to give you a couple of things you could potentially do on your own. Very nice database is the FRED database. Obviously, the Federal Reserve has consolidated a lot of different data sets and made readily available for free. We are funding it with taxpayer dollars, so you can please use the service for free. You can go in and download all the data you require. You can specify the time window and get the required graphs. It also provides you rich visualization capabilities, so you can actually access this beautiful analytics without you having to spend a dime. So please leverage this appropriately, because you have a lot of access to data instead of just trying to figure out what can be available through a paid service. So that's one thing you could potentially use. Secondly, we'll kind of contextualize it with the application we have at hand. So I'm going to ingest the data. For the purpose of this demo, we didn't go into FRED. We could have gone into FRED. We just went to Yahoo Finance, because Yahoo Finance is available throughout the world, and you can access data for free through Yahoo Finance too. For this toy problem, we just got the data from Yahoo Finance. So we're going to get programmatically the data from Yahoo. We're going to clean up the data a little bit so that we can go and filter out the components which we want, especially things like closing prices, opening prices, et cetera, et cetera. And then we will think about, well, I have a bunch of stocks, and in this particular case, the universe of 30 stocks from the Dow Jones Index. Can I cluster them into different buckets? And we will apply a couple of different clustering methodologies to figure out how the results are going to look and how can I interpret these results. And then I'm going to give you some visualization tools to understand what you're actually doing. And then I'll give you an example on how this could potentially be deployed. Okay, so in terms of clustering methodologies, I'm going to talk about 2 methodologies. I briefly introduced clustering in the prior segment. So here, we're going to start asking, the first thing you need to start asking about when people talk about clustering is, what's the distance measuring? Or what's the distance measure? So there are various methodologies which are there to figure out whether 2 stocks or 2 assets are similar to each other. One common way of looking at it is just looking at correlations, but just by looking at correlation, you may not really get all the answers. So there's been some research on various other metrics you could use to compute distances. And in here, when you're trying to bucket stocks, you don't look at just 2 stocks in isolation, right? You're doing what is called as pairwise comparison. of the distances between a stock with the rest of the universe, and then figuring out which stocks or which buckets should I be putting myself into, right? So if I'm looking at the Dow Jones Index and I take Apple, and now I'm going to be thinking, well, who should Apple be associated with, or which bucket should Apple be associated with? So in order to do that, I have to figure out, well, is Apple similar to Intel? Is Apple similar to Boeing? Is Apple similar to ExxonMobil? So I have to start asking the question, 29 times in a Dow Jones bucket, and then figure out who my closest friends are, right? So that's where the distance metric becomes extremely important. But I've given you a link to a paper by Magna in 1998. So there, in that paper, they talk about using 1 minus correlation squared as basis of making distance metric. And once we do that, we're going to use hierarchical clustering, which is an agglomerative clustering methodology for building out your tree so that you can figure out, based on how deep you want to go. If I just want 2 clusters, I can draw a line in here, and I have 2 clusters of stocks. If I can go down, I can chop this tree in here. I'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different clusters. And all these nodes, these leaves will basically have a bucket at the end with different stocks, and you'll have like 10 different baskets of stocks you can work with. So depending on how many baskets you want, you can start thinking about pruning your particular tree. And that's one methodology we're going to look at. Another methodology is a little more complicated, and I'm going to try and, in the interest of time, give you some links so that you can understand what's actually happening. But this is another way in which you can think about distance, which is leveraging the covariance matrices. And then we are going to look at affinity propagation as a methodology for clustering. And the notion here is you don't need to give in. I'm going to give you a little more details in the next few slides. But the notion here is we are going to look at this notion of, am I close to, it's basically message passing between 2 different stocks and figuring out, how close they are. And if there is reciprocation between other stocks, you're going to start putting those buckets together. And then we're going to look at how do we visualize this, and we're going to use a simple manifold learning methodology to visualize this. So the end result of this exercise is, first of all, in terms of visualization, we want to get to, this is the Dow Jones Index, right? So this is basically the correlation matrix. So if you just do a simple correlation matrix, can I understand the relationship between different assets is, a good place to start. And then we compute the distance metric, and then figure out like how can you interpret the distance between 2 different stocks. And then we start thinking about visualizing these relationships, which is a way of figuring out, can I look at the linkages between 2 different stocks and see which ones are closer. And the output, for example, in here, Microsoft and Visa were very close to each other in terms of performance, and Exxon and Chevron were very close to each other. And I'll show you in a live setting, in a demo. Okay. So this is the tool we're going to use, and I'm going to switch gears in a bit and show you the demo. So let's get to the demo. By the way, many of these things are predominantly open source. You can just go online, and I've given you a bunch of links. We didn't create everything from scratch. We leveraged existing libraries, existing demos which are out there, and then packaged it into a case study. So I'll give you some links which could potentially be used for reproducibility. Okay, so let's get to the sandbox, and this is what I was talking about when I initially told about like the videos and the slides all in one place. So what I've done is I've run a lab, and I'm going to give you the demo of the final output, and then we will kind of delve into the code in a bit. So this is the demo for the application. So this is where we can explore the different stocks. So I've given a time window of 5th, which is like close to a year ago. On May 1st through the end of 2019, if I had this as my data set, and I can potentially explore different stocks, for example, Boeing, now that we are all staying in place and not thinking about airplanes outside, when airplanes were extremely popular and travel was extremely popular, it was trading at like $300, $350, etc. So in this time frame, if I had done clustering, how would it have looked, right? So we're going to run a hierarchical clustering algorithm in here. So in this particular case, first we started thinking about the correlation matrix based on the returns of each, the daily returns of each one of these stocks. So I'm going to expand this a bit so that you can see it a little bit closer. So if I look at different stocks, you can see that ExxonMobil and
Sri,
Chevron.
sorry, can I just interrupt for a second? I don't think your screen has moved on. We're still on the demo slide.
Okay, so let me just see. I'm sorry about that. I didn't realize that. Give me 1 second. Okay, so is this clear now? Can you see my screen now?
Yep.
Okay, sorry about that. I think there was some, okay, so this is basically what I was just saying. I'm gonna step back a minute. So when I go into the sandbox, which is where you're gonna start out with if you wanted to try out this demo. And when you go down there, there is the clustering demo. So you go in here and you run this on the sandbox, and when you go in here, this is basically what you're going to see. So what we did was we explored the stocks, which was to specify a time window in which we want to get the stock specific details. And this is what we're seeing in terms of the prices. And when we talked about Boeing, so I was telling you that if I looked at the Boeing data, as we were trading at for like 350 or so when we were traveling, life was all good. And if we thought about hierarchical clustering for this time window for all the 30 stocks, this is going to be the correlation matrix, right? So we have taken all the 30 stocks, and this is what we see starting from 3M going into Walmart. Okay. Now this is the one I was telling you a little bit about. So here, what we are seeing is the correlation matrix with, it's an annotated heat map, as it's called in the Python world. So here we are looking at, let's say, for example, this 0.8, which is darker compared to other cells in here. So this is where we are looking at ExxonMobil and Chevron. They have a pretty high correlation. 0.9, JP Morgan and Goldman Sachs, they're pretty high in correlation. So when you think about like similarity of stocks, this is a rudimentary tool you could use for figuring out similarities. But this is where we computed the distance metrics, wherein we looked at 1 minus the correlation, and we computed this distance metric. And the intuition there is, if I look at a heated map in here, going back to the same ones, if you look at Goldman Sachs and JP Morgan, you see that the distance is 0.3. Compared to all the other distances, this is the closest, which is, it means that the Goldman Sachs and JP Morgan are very close to each other, right? And then if you look at some additional ones, like for example, this is 0.4, which is ExxonMobil and Chevron. So the distance is very close. So this matrix, the distance matrix, will tell you which stocks are close to each other, right? And this is going to be the input to compute the linkages and draw out your hierarchical clustering dendrogram, wherein you can see that the Intel and Apple are in the same bucket, if you will. Chevron and ExxonMobil is in the same bucket. And then when you think about pruning it at this level, you're going to see a lot of buckets with these stocks in here. This is going to be a one bucket, this is going to be another bucket, this is going to be another bucket. But you could reduce the number of buckets by pruning your tree somewhere up in here, which will basically bucket. For example, if I prune somewhere in here, now American Express, Microsoft, Apple, Intel, and Verizon in that time frame will all be in one particular bucket. Okay? So this is just using the hierarchical clustering methodology as a basis. And now the other method I told you about is affinity propagation. And I'm going to show you the code in a little bit, but let me show you the demo before moving into the code. So if I'd use the affinity propagation methodology, the good news is in k-means, you have to specify the number of buckets you want. K stands for the number of buckets. And here, you can just run the algorithm and it will generate the best number of buckets in here. So you can see that, for example, in the 6th bucket, you had Coca-Cola, McDonald's, Merck, Pfizer, Procter & Gamble, Travelers. They were all kind of in one bucket. And in this other bucket, you have Intel and Dow and Caterpillar and Walgreens. but then you had in the third bucket Goldman Sachs and JP Morgan all together. So you could basically use this as a means of testing out which clustering methodology makes sense for you from an analyst perspective. And this is just a visualization using manifold learning to, first of all, plot out the linkages, but also build out like a scatter plot, which renders the stocks which are close to each other close by. So for example, you could see JP Morgan and Goldman Sachs are close to each other in here. Microsoft and Visa are close to each other in here. And then ExxonMobil and Chevron are close to each other in here. So this gives you a visual way of basically looking at the world you're working with and then figuring out either in terms of stock selection or in terms of analysis, looking at those buckets and working with that analysis there. So that's the demo. But let me kind of give you a little bit of under the hood thing about how it actually looks when you actually build it out from scratch. So I'm gonna just show you what is called as a Jupyter notebook or the Python code behind the scenes. What you had to go through in order to build it. So this was just an example notebook we wrote. We used a bunch of packages like yfinance and NumPy and Plotlib, Matplotlib and Pandas. So these were the 30 stocks, and I built in the exploration. I somehow like Boeing. I was looking at the stock for a while. So this is the Boeing data which I explained, and then here is the data frame for the various prices. I computed the returns. I built out my correlation matrix. I visualized it, and then looked at the distance matrix in here and visualized the distance matrix in here, and then thought about the hierarchical clustering aspects of it in here, and then looked at this notion of affinity propagation, wherein we first actually did not just look at the closing prices, we computed the variation of the difference between the closing and the open prices. Now, this particular example actually is available with scikit-learn. So when you download scikit-learn, you actually get this as a part of your package. So you could definitely look at the website to get some more details about how the various algorithms were used. And we basically use this graphical lasso CV algorithm to build out your covariance estimator. And the point here is we are doing L1 regularization. I'm not going to go into details in here, but it's basically lasso regularization. And we also do cross-validation because you have to choose the alpha parameter, and you can explicitly provide the alpha parameter for L1 regularization. But here we are letting the cross-validator do its job to come up with the best possible alpha parameter. And that's the reason why it's graphical, lasso, and CV. You also have just the graphical estimator if you wanted to use without regularization. Okay, so now that that is available, we basically used that and passed it to the affinity propagation algorithm. And this is where we were talking about, and I provided you some links. So if we just take this link and then paste it, sorry. Okay, so this is the affinity algorithm. As I mentioned, it's about sending messages between pairs of different samples until there's convergence. There's a nice paper available along with that which details this particular algorithm. But if you're using scikit-learn, it's just a simple call of a function and saying that this is what I'm going to pass in the output of this edge model covariance matrix. And then I'm going to get my specific clusters in here. And then I'm going to do the manifold learning visualization, which is non-linear dimension reduction, so that we are taking all these features and then we are basically projecting it on a two-dimensional plane. And when we visualize that, this is basically what we get. Okay, so this is me being the data scientist or the machine learning person thinking about this entire workflow. And once I build this out, I take this and I contextualize it in an application perspective, and I make it available as a demo for my end user. So my end user doesn't have to think about all the Python code which goes behind the scenes. They are basically choosing the different assets, providing the different timeframes, and then experimenting it to understand what's actually happening. That way they can do their analysis. Okay, so that is one application I wanted to give a demo. Give me one second. Let me just look at the time. So let me kind of talk about the second demo, which is in the context of natural language processing. And then I'm going to break for a few questions. So this is going to be a very quick overview on natural language processing. So here, the big picture notion is, this was 3 or 4 years back when we were doing a boot camp on neural networks and deep learning in New York. So we had many participants from different companies, from Bloomberg, from Capital One, from JP Morgan, etc. But then we also were curious because there were 6 scientists, data scientists from JP Morgan, all at the same place. And they were all specialists in natural language processing. And I was curious and I asked them, and they said, well, we have a lot of text-based information. We have built out a whole data science team to leverage all this text-based data and then build out decision support systems. So a lot of companies are using natural language processing as a way of not only tapping into the structured data sources they have, they're also leveraging their unstructured data, which could be in terms of reports, in terms of call transcripts, in terms of communications with clients, and trying to make sense out of it. In the technical world, you see a lot of process automation. For example, when you try and use your online tech support, when you're typing in things, most likely the first interaction you're going to be having is not with a person. It's with an algorithm, which is using natural language processing to understand what you're trying to do and either answer it for you if you are looking for instructions on how to reset your password, or if you're looking for a particular place in which you can upload your documents. So it's going to give you those answers without a human being involved. Or if there is human involvement required, it basically sends out that request to a human. In the context of financial services, we have a lot of data, and the scenario we are kind of envisioning is.
Sorry, Sri. Okay, I think we're just behind on your slides again.
Oh, I'm so sorry. Let me kind of. I'm actually just going to share my entire screen. That way, I don't have to do the switching. Okay. So is this good now?
Yeah.
Okay. Perfect. So I was just at the screen. We didn't move anywhere further in here. So this is an example of the earnings call transcript. And we're imagining a scenario wherein there's a portfolio manager who is maybe having a watch list of maybe 50 stocks. And every quarter, the portfolio manager would be interested in kind of getting a big picture on what was the sentiment in this earnings call. And one thing they could potentially do is go in and listen to the call themselves and make that analysis, or wait for a few days for their favorite analyst to write out summaries or look at the news the next day and try and understand the sentiments. But also, you could have decision support systems which does some of the work automatically for you. And this rudimentary tool we are exposing or building out as a part of this demo is to just let you know that you don't require rocket scientists to build out this whole thing. With readily available tools, you can build out a basic sentiment analysis engine with very few lines of code, in fact. Okay, so let me kind of walk you through some of the challenges on why sentiment analysis is a problem. Of course, we always have challenges interpreting emotions, and labeling of data is extremely hard, especially in the financial services world. So many a times the analysis becomes hard for machines to really think about what the sentiments are when we are looking at data sets. And natural language processing as a whole is this confluence of different technologies, leveraging computer science methodologies, artificial intelligence methodologies, linguistics methodologies. And what we have done is build out this huge portfolio of different applications which are coming in handy. Now, it could be simple things like question answer systems, topic summarization systems, classification methodologies, information gathering or tone analysis kinds of mechanisms. But the point is, there are so many applications in natural language processing. And in finance, we are seeing things like Erica, which is a chatbot Bank of America uses, and JP Morgan software, as I mentioned, they took what lawyers would have potentially taken a really large amount of time using streamlined systems. They could streamline many of the processes out there. Now, many of the challenges we deal with on a daily basis, right? So when we talk about interacting with a Google or Alexa, without we explicitly asking it to use a natural language processing system, we are asking it to translate, we are asking it to summarize, we are asking it to answer questions. We are basically, not only expressing what we want Alexa or Google Now or Siri to do, but we are also getting responses in a human-like form. So the technology has significantly evolved over time, because in the past, people were using these traditional grammatical, hard-coded methodologies for processing text. And what has happened now is, with the advent of deep learning, we have seen a whole evolution of way in which natural language processing has happened over the last 10 to 15 years or so, leveraging techniques like Bayesian networks, neural networks, semantic networks, et cetera, et cetera. And the various challenges which we thought we had in terms of language, because the way we express our thoughts depends on the context in which we use it, right? So, for example, if I say something like Jaguar, Jaguar could be the animal or Jaguar could be the car, depending on the context of how I use Jaguar. So there's a lot of nuances when we think about language, and it becomes a big challenge on how do you address all these problems. And that's the reason why building text-based analytics or natural language processing analytics is extremely hard. And typically companies should have a large amount of data in order to build really productive natural language processing systems. And many times we don't have it because we have very limited amount of data. And that's the reason why we always have to rely on experts. Many times natural language processing systems fail because we haven't trained it well enough with contextual domain-specific data. And secondly, we don't have the experts to go in and do the labeling. For example, if there was in an earnings call a statement talking about a particular quarter's performance, now whether that statement was positive or negative, it's very hard for an algorithm to decipher. But if there was a human analyst who has context on finance, who has context on this company's performance in the past quarter versus this quarter, it would be pretty easy to decipher whether that particular statement was a positive statement or a negative statement. And hence, in various areas, it has to be humans who will have to do the analysis, and you can't entrust those to natural language processing. And I hope this example I'm going to show you will tell you a little bit about challenges, because many a times, we are sought out by some of our customers to say, well, we're trying to get this natural language processing in-house. Can you do some due diligence with that? And when we look at some of the capabilities, it kind of works really well in some example use cases, but in some complex use cases that potentially would fail. So there are various options, right? So you can potentially go in and ask humans to do the analysis, which you typically do. We pay a service and we ask our analysts to send out reports to us on a regular basis, which will tell us summaries about how the call went, and based on the expectations, what does it actually mean to the stock price. We could hire those experts in-house to contextualize and build the research in-house. That's where portfolio research comes in, right? Many times we also leverage factors which are available through various vendors, and we basically bring those factors to talk about sentiments about various factors. So let's kind of build out a simple application just to kind of illustrate how we would have done it had we built it from scratch. And I'll tell you a little bit about the challenges we'll have to deal with. So in the context of what we are doing, we are getting this EDGAR data, which is the filings data. And think about, this is the assignment I typically give my students so that they understand the pain of working in the real world and not just working with textbook data. So this is real world data. We go into the EDGAR database, get a transcript of a real earnings call. And now we need to think about, how do I do sentiment analysis on it? And the problem of doing sentiment analysis on something with real world data is, the biggest challenge we have to deal with is, I don't know how to label it because I don't have an expert in-house. And that's where you can think about leveraging some of the APIs which are out there, and you could potentially train your own algorithm to do the labeling for you. But many times you could start out with some of the readily available APIs out there. For this purpose, we actually tried and compared 3 different APIs. One was the Amazon Comprehend API, the Google Text Analytics API, and the Microsoft API. And we asked them to, we'll give you a statement, you tell us what the sentiment is, and we thought we'll summarize it and just present it for you. So it's kind of an exercise to do the labeling through some of the readily available services out there. And then you can think about building out your own sentiment analysis model. So let me show you a demo on how it's going to look, just to give you a feel for how easy or difficult you may want to pursue in terms of perceive in terms of thinking about natural language processing systems. So I'm going to show you this demo of building out a classifier. So let me, this is the EDGAR sentiment analysis demo. So let me start with the demo and I'll briefly show you the code if we have enough time. So this is the actual application. So here, the two inputs I will need to go in and scrape data from the SEC website where the EDGAR filings are the CIK number and the accession number. So these are the identifiers for that particular statement. And what we will have to do is basically generate a URL so that we go in and get those two, passing those information, get those documents we have. And then what we do is we are going to call the APIs, and we'll have a choice of these three APIs. And let's say I start with Google. So what I'm doing now is I'm going into the SEC database, getting the statement which is identified by the CIK number and the accession number, getting it, doing some basic processing. I'm not going to do a lot of processing. I'm just going to take some of the extraneous, special characters out. I'm going to arrange them so that I have proper lines. And then I'm going to take all these and then ask Google that I'm going to send you one statement at a time. You tell me what the sentiment of that statement is going to look like and keep on doing it for the entire document. So this is a prototype application, and that's why you see this running on the top. So it's basically doing the job of sending this data and then bringing the sentiments back. So it's going to take a little bit of time. So here, one thing to note is we have multiple vendors. So you have Google, you have Amazon Comprehend, we have Azure. They all provide APIs. So it's pretty simple to do sentiment analysis by just passing them with the interaction to the API. So here is what we are seeing. So you are kind of seeing most of them were neutral. It's very close to 0. And some of these statements were negative and some of these statements were positive. So here, again, the notion here is, we actually got the little bit of preliminary analysis. Now we're going to do the same thing across the board and try and compare it with all the three vendors. So this is kind of the summary analysis. So when we took the same document and we sent it to 3 different APIs, and we can see that this is basically red is Google, blue is Amazon, and then green is Microsoft. For the same data, Amazon said only 20% of the data was positive. Google said 40% of the data was positive, and close to that, Microsoft said 40% was positive. Amazon said most of the data, most to 75% of the data was neutral, which is basically to say I'm not able to decipher the sentiment of what you're saying, so that's why I'm just going to bucket it into the neutral category. And then very few of these statements were deemed as negative. So for an analyst, it could be that this is going to give you like a big picture orientation of, well, what the statement or what the call transcript had in terms of the positive versus negative versus neutral sentiments in the document. And here are some more statistics in terms of the distribution. And I could extract some statements out in here. So for example, this statement in here was termed as the most negative statement by Google. Reported revenues for our peripheral business declined in the mid-single digits in Q1. However, after adjusting for the discontinued product lines just mentioned, our peripheral business grew in high digits with single double digit in FA and DCB products. And Amazon and Azure deemed these as neutral, but Google termed it as negative. So this is where you're going to test whether, if I can build like a decision support tool, wherein the most positive statements or the most negative statements could be summarized for me, which will help me get a big picture of, does it matter for my portfolio or my investment decision, whether these negative or positive statements are going to materially affect my current portfolio or change my decisions in terms of my investment strategy. So it'll provide you natural language processing and provide you some of these additional tools in order to facilitate the discussion either internally or through an automated tool like what we just saw. So basically, what we're going to do is, in the context of building it out, I'm going to not give you the under the hood tour, because that actually, in order to build this out, we actually had to write different notebooks, or we had to like 6 different programs, one to go and crawl the data from SEC's database and get the data, and one to pre-process the data, do the sentiment analysis on Amazon, do the sentiment analysis on Azure, do the sentiment analysis on Google, and then build out the comparison script to compare all the results. So it requires some aspects of it. So full-fledged machine learning course, like we are planning to do from next week on, which will run for like 8 weeks, we'll give you those nuts and bolts on how to do it. But just to give you a perspective that it is feasible, but also it requires a little bit of understanding how to work with the various moving pieces. So to summarize, what we tried to do was build out a natural language processing pipeline with publicly available data, with services which are readily available for access. And we didn't try, have to write a lot of machine learning algorithms, but we had to understand what we were trying to do. And we were trying to do the labeling part. And we actually have a full-fledged case study, which is beyond the scope of this introductory webinar, wherein we take these labeled data sets and then use additional methodologies for building out a whole service for yourself so that you can fine-tune it and use it for your internal analysis. It's a very fascinating field. If you're interested in it, I would highly recommend take some of the courses or materials which are available online to build your expertise in unstructured data and using natural language processing. So the 2 applications we talked about, one was with respect to unsupervised learning, which talks about clustering. And the second use case is natural language processing, which is to build a sentiment analysis engine, which is basically a classification problem. So given statements, it'll tell you whether it's a positive or negative. And guess what? Most of the services we were using in here are based on neural networks. And we did not have to build any neural networks. We're just leveraging the neural networks, the very complicated neural networks Google has, Microsoft has, and Amazon has. And they've been tuning these algorithms because of the tons and tons of data they've been collecting from all of us. And all the data is used for building out their sentiment analysis engine. And we actually used a huge neural network, which we can't even imagine, by just calling their API and getting requests back, as in terms of responses. So I hope that kind of gave you a perspective on some of the practical applications of some of the clustering and other use cases. So I'll pause here for a minute before we kind of do a recap, and I'll talk about some of the frontier areas. Richard, so we can go back.
Great, thank you. Excellent. So a theme of questions actually is about how you train your neural network. Mm-hmm. So what's the nature of the data? How do you make decisions about what kinds of variables to input into it? And also for data sets which are a time series, then just how much time should you be looking at? You gave an example earlier of equity market data. So yeah, what are the the kind of the models you have for thinking about how you train a neural network?
Sure. That's a very complicated question. It's a whole semester course.
Okay, right.
There isn't an easy answer to just basically say that's again a science, right? Because that's where data scientists build their proficiency. And nowadays you have graduate programs training people to think in that thought process on how do you build out your data sets in the first place. So let me kind of simplify this for you a little bit. In the context of equity and time series data sets, you can't, the way I usually think about the world is if there are existing methodologies which work really well in terms of ARMA or EMA, the time econometrics methodologies which we typically have, and it works pretty well, I usually start with those. I don't start with a very complicated neural network. Because in order for me to have the neural network understand this notion of cyclicality and trend and all these other aspects, I have to provide a lot of data, right? It is possible, but why try to make the neural network learn things which could easily be modeled based on human intelligence, right? But if there are things which are extremely complicated, which our simplistic models are not going to be able to factor in. So there are algorithms like LSTMs and RNNs, recurrent neural networks, which are typically used for temporal or time series-based data sets. But I also think about if I can convert temporal data sets to cross-sectional data sets, that have a lot more leeway in terms of modeling. And that's where I think about windowing and think about moving averages and windows and slices, which I could use, and think about if I had data of the last 15 days, can I project something for the next few days? And when I build my energy models or energy forecasting models, so I build out like a long-term forecasting model and a short-term forecasting model. In the short-term forecasting, I'm trying to forecast what is the energy needs for the next few days. In the long term, I'm thinking about what's going to be my energy need for the next year or so. And they would be different models. In the neural network context, I'll be leveraging a lot more data to do my long-term forecasts. For my short-term forecast, I'm just going to use the short-term data, and I'll use just the slice. And I could basically structure my entire time series into slices of windows and basically use it in a cross-sectional context and then build out my models. So there are various tricks you could potentially use. In the context of natural language processing, there's this whole notion of feature extraction and embedding. And that's a whole science by itself, wherein you basically take all your text and then kind of convert them into these rich embeddings, which are very dense, and then use those embeddings for building things up.
Okay.
I'll stop at that. I can keep on going for the next few hours, but
that's okay. Excellent. And there's one related question. There seems to be, just judging by the kind of the comments, there's a degree of skepticism about natural language processing. What's your view on the state it's at right now?
Yeah, so I would say we're not there yet, which is the good news and the bad news. The good news is there's a lot more areas for research. So, we can have better Alexas, better Siris, better Google Nows. There were a bunch of late night comedy snippets wherein they were, with the COVID-19, people were using their Alexas, trying to make it say words like yoga. And they had to give in a statement and, make Alexa say yoga in the statement. And they were just having fun. It was not at all feasible. Then finally, I think one of them said like, okay, so it was sounds associated with the bear, and then said maybe Yogi Bear, and got close to yogi instead of yoga. But the point is, in all seriousness, especially in domain-rich languages like healthcare and finance, wherein context is extremely important, we're still scratching the surface of using natural language processing. Because in order to interpret a statement, which an analyst can look at it and immediately make a judgment whether it's positive or negative, or does it have any material information in here, we require so many more pieces rather than just the interpretation of one particular statement. And to build a context for a generic natural language processing engine is extremely hard. However, there are advantages of topic summarization, natural language processing. Twitter data, if I'm kind of launching a product, or if a company I'm watching has launched a product, and if Twitter sends out things like it was actually followed by these hashtags and these other influential people retweeted it, and the discussion has gone exponentially on that particular topic. Now that's there. That actually tells about the potential significance of that piece of information. Either it could be an entertainment company releasing a new video or signing up with a new artist, right? So all those would materially impact that particular company's stock. And it's impossible for an analyst to sit there 5 days later trying to take all the numbers from Twitter and add it up. So that's where things like natural language processing will come into play, wherein you can summarize these analytics and kind of say, compared to, Adele's last song, which was released 2 years ago, and if she makes an announcement now and it had this delta in terms of performance, what does it actually mean for that brand she's representing, kind of a thing. So there are some opportunities, but we're still not there yet. Great,
thank you. Okay, so back to you for the last portion.
Absolutely. So let's kind of summarize it in the next few slides. Give me 1 second. So I'm going to switch to. Okay. So in the last, it's like more than 3.5 hours now. In the last 3.5 hours, I hope I've excited you enough to consider machine learning and artificial intelligence seriously. If you have not looked at artificial intelligence and machine learning, it is going to have a significant impact on your careers over the next 20 plus years for sure, because of the way in which the areas have changed in the last 10, 15 years or so. So even if you choose to ignore it today, you will be confronted with the reality that many of the technologies we are talking about today are going to either augment the way in which you do things, or unfortunately may replace the way we do things today. So it's a good idea to really have a good idea about what's all actually happening in the world today. That way you can figure out how can you be educated, how can you be connected with the profession, especially in financial services, wherein we deal with contextual data, the velocity of the data, the variety of the data, the volume of the data, and it just has been growing significantly. And the way we are connected with other parts of the world today, things which happen in other parts of the world will definitely matter to all of us. So definitely it's something you have to consider. So what are the movers and shakers or the frontier areas which are happening? I mean, we have seen a lot of new innovations, but we have also seen a lot of new frontier areas, which is one, making life simpler for us, especially when it comes down to building more richness in terms of analysis, building more rigor into our analysis, having different tools in which we can process things which we have never processed before, and having means by which we can make our results, we can really use some of the outputs based on the analysis we have done. So that's one way to look at it. But there are also some themes which are significantly changing the way the world is going to operate in the near future. And I'm going to give you a few tips on how you can potentially think about these if you're interested in learning more. So the one area, as I mentioned, is neural networks, which has seen a significant uptake in terms of interest and also applications. The good news is the Silicon Valley, companies like Amazon, Microsoft, Facebook, all these companies have invested significantly in terms of research infrastructure. And you have graduate programs specializing with graduate students studying these and publishing papers. So there's a lot more focus in terms of research, and we are only going to see some of these techniques mature in terms of applicability and a lot more novel use cases, which is going to make intelligence, which is going to be artificial intelligence, practical in various aspects. Now, in addition to that, some of the process aspects wherein we had to do the due diligence, wherein when it comes down to non-machine learning professionals trying to pick up machine learning, the biggest question is, does everybody require a PhD in machine learning in order to use these algorithms? And the answer is no. And the reason is we are seeing so much maturity in terms of ecosystems that this whole tooling has also caught up, and this notion of automatic machine learning, wherein you leverage hardware to do the experiments for you, and you have a choice. Instead of you doing 10 experiments by manually picking settings for each one of them, you basically have algorithms do these tests for you and tells that, well, based on the budget you gave me, which is to run for an hour with all these potential choices, this is the best possible choice you have. So that's another beautiful area. And in fact, you are already seeing this in action. Things like DataRobot or H2O, Azure ML, Databricks, they all have automatic machine learning based offerings. And it's also a good place to start, especially if you are not going to be writing code in Python and starting from scratch in the first place. In addition to that, there are tools like Amazon SageMaker and Google AutoML, wherein they don't give you the behind the scenes architecture on how it actually works. But if you're comfortable using a cloud-based offering, you could potentially use those services to get the results. Secondly, there are, there's a lot of interest in this notion of ensemble learning. And it's basically a notion that instead of you doing one test at a time, how about we leverage multiple experiments and then combine the results and get high quality results in the combination rather than just taking individual cases. And there are a lot of ways in which you could do it: simple weighting, or Bayesian averaging, or building out random forests and trees. So there are a lot of different algorithms you could potentially use. The con here is the moment you start building multiple components to, using multiple components together, you're going to suffer with respect to interpretability, because now you're judging the results based on a committee decision of various algorithms, rather than looking at the individual decisions made by each one of these algorithms. As we were kind of mentioning, there were a lot of frontier areas, and natural language processing is actually going to be a huge frontier area because we're just scratching the surface on what's feasible with natural language processing today. And when we start seeing, larger applications and contextual and domain-specific machine learning as a service come into play, financial services firms will have the opportunity to either use labeling services through natural language processing or access different kinds of summarization and Q&A services through various natural language services which are going to be available. The one thing to note is building natural language processing in-house is going to be extremely hard, especially with the requirement of large amounts of data sets out there. So that's a very hopeful area to be looking at in terms of natural language processing. Anomaly detection is actually going to be huge. So we have seen a lot of successes with anomaly detection. In fact, I had a client project wherein the client was actually having 3,500 rules for tracking any kind of fraudulent activity. And just imagine you going into a restaurant and using your credit card, and an institution is running that transaction through 3,500 different rules just to make sure that the transaction is not fraudulent. And machine learning has a huge area of advances in the context of fraud detection and anomaly detection. And the reason being, we have a lot of transactions, millions and millions of transactions. So algorithms can uncover these hidden patterns which are there to figure out anticipatory fraudulent transactions so that you could either block those transactions or at least pause them till you are confirming whether the transaction is fraudulent or not. In addition to that, there are a lot of applications like insider trading detection when you have certain transactions which are not normal passing through various channels, but also graph-related anomalies wherein you are seeing certain activities happen in certain areas could be another area which could potentially be helpful. And we have also seen a lot of interesting applications in the context of AML and also other areas wherein anomaly detection could really come in handy. The last area I want to talk about is this whole notion of model risk management. In the last 6 months or so, we have worked with a lot of different customers, and predominantly we have seen this huge influx of newer technologies come into the financial industry, either through open source technologies or machine learning products, data mining and data science related products. And it's challenging the industry to think about how do you manage risk with the whole different tools which are coming into play. Now, we are all meant to be fiduciaries for our clients and for the investments we are managing, right? And we have to take it very seriously to understand not only the benefits of these technologies, but also thinking about what are the problems which these technologies could potentially pose, and do we have the in-house risk expertise to be able to handle these problems which could potentially crop up? And also, do we have good governance structures to really assign ownership to the various processes in play so that it doesn't just become a cool and interesting thing to do, but it's also a responsible thing to do to make sure that you're also managing and understanding the risk aspects of the various pieces of the puzzle. And the reason being, a model is not just the statistical model. You have 4 major components of a machine learning model. You have the data, lots and lots of data, different varieties, different volume, different kinds of velocities at which data is coming in. But you also have different levers you're working with in terms of models, the parameters, the hyperparameters, the various specifications which are potentially there in the model. But then also you're getting all these programming environments. You have Python, you have R, you have SAS, you have MATLAB. Now you have this whole confluence of different tools different users are using. And then you have these interdependencies wherein you are either relying on a vendor to give you some factors, you're using the database team's inputs, and then you're expecting the analyst to collate all the information and make these decisions. So the whole modeling piece is not only in the context of the financial services world, and this was a nice paper called as the hidden technical depth in machine learning systems, which Google and a bunch of researchers at Google wrote in 2015, where you could see that the machine learning is only a very small piece of the puzzle. You have all these other pieces of the puzzles which need to come together to have a successful implementation of machine learning system. So I hope you take away from this session that machine learning is not all about Jupyter notebooks. You have to have the right kinds of ecosystem and the culture within the organization and the investments to make sure that the machine learning application is going to be a successful production application. Along with that, you have to think about reproducibility. There was a nice paper in the context of science which talks about this whole notion of reproducibility crisis, and especially when you're using machine learning models wherein there are a lot of different applications coming to play, you have to think about reproducibility too. I was at a recent model risk conference wherein the model risk head at a company spoke about the challenges she was having with just trying the model risk management team to be able to reproduce what the modeling team had built. So even within a company, if the folks who are working in the same domain cannot reproduce each other's results, it becomes a challenge to think about having a concrete process to make this available to the outer world and for other potential stakeholders. So it's important that you factor that in from a risk perspective when you're building in machine learning challenges. So we wrote a paper just to talk about the 10 different things you could potentially do with respect to governance in machine learning models. It's available in your slide deck. And if there are any specific questions associated with these, please do reach out to us and we'd be happy to talk more about it. But the point here is we have evolved from machine learning as just a cool art/science, which is predominantly going to be focused on, smart machine learning and quant professionals building models, to thinking about it as a process which needs to be managed at an organization level, and what are the various components and tenets you have to factor in to have a successful machine learning practice within your organization. Okay, so now that we have understood some of the frontier areas, I'll take a quick few minutes to talk about 10 things we want to take away from this whole 3.5-hour, 4-hour presentation. The first thing to note is it's not always about your machine learning algorithm. It's about the business problem you're trying to solve. If you don't have a good business problem to solve, machine learning is not going to help you if you have not really thought about the problem you are going to be addressing with machine learning. Second thing is it's all about the data. If you don't have quality data sets, if you don't have the right kinds of data sets, the machine learning apparatus and mechanisms are going to be useless. So you need to have the data right before you can get your machine learning problems solved in a good way. The third thing is you need to not only have the data, you need to have a good data processing strategy. If you don't have a good data cleansing team or a data engineering team, the scientists and the quants are not going to be doing all the cleansing and building out the models themselves. They need a good backend support to get all the data in so that they can start working with the quality data sets. The fourth thing to note is you really need to understand the data. It's not just about building out an automated pipeline and forgetting about it. It's about thinking about how can you structure your process and understand the nature of the data before you can start filtering out and thinking about missing data, thinking about the feature engineering and all these key aspects before you can start applying it into machine learning problems. The fifth thing is you have to define the goal on what you're trying to do and why you're trying to do it. Is it because you want to reduce the costs? You have to get some kind of a competitive advantage? You want to reduce the risk? Why are you trying to build out this machine learning model, which will define the investment and the time you're going to be putting into the whole process? The sixth thing is do not ever just shortlist, just think about a few algorithms and say, well, I'm going to use all these algorithms and that's it. Because the algorithms are tools and you have to apply the right tool to the right job. And you should have this whole portfolio of tools available, but you're going to be shortlisting them and using them contextually, not just picking an algorithm and then applying it to your data set. The seventh thing is, as you mature your adoption of machine learning, you have a lot of different things to think about. Am I going to be running it on my laptop, or should I be running it on my cluster in my office, or should I be running it on Amazon's web services? Should I get everything done on my end? Should I hire a machine learning professional? Should I outsource it? Should I give it to Amazon or some other company to do the service for us in terms of machine learning as a service? All those things need to be think about, especially when you're moving beyond working in your local context to adopting it within your enterprise. And some of the process-related aspects, though not something you think about when you're building out machine learning models, because it becomes important when you're scaling up your machine learning practice. And that's another important thing to note. And the ninth thing to note is the machine learning algorithms come with a lot of levers. And you need to understand and operate the right levers in order to make sure that you get the best value out of it. If you just take the default settings, think of it as you're investing in this $10,000 really expensive digital SLR camera, and you're using auto settings and you're not leveraging any of the other settings out there. So the default settings don't really matter for machine learning setup. You need to really understand the levers at hand. And then the last thing is there is a lot of aspects with respect to governance and risk which needs to be factored in, especially with so many moving pieces. So you need to have all the stakeholders involved so that you understand the whole process and you make sure that the right responsibilities are put in place before you can productionize applications. Oh, there's one more. Machine learning doesn't stop at the deployment of the model. Your journey starts. You need to really monitor your processes to make sure that it's not stale and it's efficient as you go and you're really getting the value of the application. So you need to have a good monitoring system to leverage the whole ecosystem out there. So I'll kind of stop with the last slide. Think about it as a whole workflow. Many a times my students focus on this piece, which is the supervised and the machine learning pieces, and here supervised, unsupervised learning pieces. But there's a lot more to the whole machine learning workflow. If you're learning machine learning, you need to understand the whole picture rather than just focusing on the core algorithms, because 80 to 90% of the work happens outside of just the algorithm choice. Okay, so to give you a quick recap of what we did in the last 4 hours or so, in the first session, we talked about the key trends in machine learning, talked about machine learning and fintech. We took you through a tour of what does it take to build a machine learning algorithm. We looked at 2 case studies, one looking at interest rate prediction using multiple machine learning algorithms. The second one was using a synthetic data generator and thinking about scenario analysis with respect to synthetic data generation. In today's session, we extended last week's session by talking about unsupervised learning algorithms, supervised learning algorithms in the context of classification. And we looked at 2 case studies. One was clustering for investment decision support. Another one was natural language processing to build a sentiment analysis engine. And then we concluded today's session with some of the frontier topics which are out there, including deep learning, anomaly detection, risk interpretability, model management, etc. So I hope you enjoyed the session. I hope you learned a lot. So as Richard mentioned early in the session, all these slides and the videos are going to be available to you. So we have Academy, which is basically where we are putting all the demos I presented to you. That way you can access it. Just use the code CFA Masterclass so that you get access to the right resources. Yesterday, we noted that people from 24 different countries had access to the slides and the demos from the last week's presentation. So would love to engage with you to help you continue your learning journey. And we're also doing a bunch of other courses through the Academy. If you're interested, you can think about taking a Python-related course on the data science front. And we are also offering an 8-week course, which is starting from next week, which will help you kind of get the learning going. And for CFA members, we are also offering a discount if you use the code 2Affiliate, which will take another $100 off. Okay, so that's a little bit about some of the courses you can potentially do. And Richard, thank you so much for your assistance through the question and answers in the last 2 sessions. I'd love to answer any questions you may have at this point.
So my pleasure, Sri. Just one final question for you. We've had a lot of people asking about how can they get into this kind of area? How can they learn the coding skills necessary to understand this? You made a point that they don't necessarily need to, but if they have an interest in that kind of an area, perhaps you could give some guidance based on your own experience. So tell me, and tell please the viewers, how did you get into this area and evolve your skill set to include coding and machine learning?
Thank you. I had to start telling my whole life story if I wanted to kind of, get in, my interest in computer science and machine learning. I think I had an unfair advantage of sorts, to be very honest. And the reason is when I did my grad study, I focused on machine learning and robotics. This was 20 years ago. And I wrote papers on mobile information processing and agent-based systems, wherein we used a lot of rudimentary agent-based systems concepts. And unfortunately, I could not leverage and use a lot of the things I learned at that point because we did not have the packages, we did not have the hardware, we did not have a lot of different things. But today, life is much simpler. In fact, had I learned it today, I would have saved so many years of my grad study, because we have open source packages like Python, which can readily make machine learning available at your fingertips, even if you have just a laptop, basic laptop, right? So you have a lot of online tools available, but you are now dealing with the sifting problem, which is, how do I sift through all the things which are out there, starting from like maybe a $9, $10 Udemy course through the $30,000 course, which Harvard and other institutions provide you in terms of analytics and machine learning related courses. So I think it's a personal decision based on how you learn. The way I typically keep in touch with what's happening is I'm engaged. I make it a point to spend at least 3 to 4 hours for my own continuous learning. Learning has never stopped for me, and that's something I want everybody to adopt, because in today's day and age, in the time we live in, the only thing which is going to be constant is change. And you have to be geared towards change, which is going to happen throughout our careers and lifetime. So a discipline to learn every week and keep our context is going to be something. And that's the whole reason why we built Quant University and the programming we offer, to make sure that we keep people abreast of all the changes, and the programming is geared towards that. But there are a lot of tools available. It requires some aspects where if people reach out to me, I'll be happy to provide some specific decision or contextual advice if need be.
Thanks so much, Sri, and thanks so much for your insights today. If you are a CFSU member, you can claim your professional learning credits by logging on to your tracking tool on your website. And thanks all of you for participating, asking questions, and being a very active audience.
Yeah, and I also want to thank you, Richard, and the CFA Institute for inviting us to do this webinar. I hope it was a learning experience, and I hope to stay engaged and stay in touch with all of you virtually.
Thank you.
Thank you.